Okay, hello and welcome to part 2 of the Chapter 8 webinar. We're still continuing on with solution chemistry. All right, where we're going to start today has to do with solubility, saturated versus unsaturated systems. For those of you in the molarity simulation lab, this will probably help you a little bit, this whole section. But then, of course, the additional information about how to actually calculate molarity, for instance, will be covered in this seminar. If not this one, then the very next one that would be after this. So let's first talk about solutions and solvation. Okay, so if you have what's considered to be an unsaturated solution, let's look on the left here. You have the beaker, and then you have some material that is being dissolved in there. It could be sodium chloride, for instance, or it could be sugar. Either one looks like it's a white powder, something that's going to be readily soluble in liquid. The solvent in this particular case would probably be water, and then the solute is either the sodium chloride salt or sugar, for instance. So if you have a little bit of solute, and if it already is favorable to enter into solution, meaning the whole like dissolves like, are the intermolecular forces going to be favorable for dissolution? Basically, do we have hydrogen bonding present? Maybe there's some dipole intermolecular forces and potentially some ion dipole intermolecular forces. So all those three would be valid underlying reasons of why one material would dissolve in another, the solute dissolving into the solvent. So that definitely reflects back on what we learned in chapter 7. So if you have material, the solute, added to the solvent, in this particular case water, if it dissolves completely, then you have a nice solution. If it doesn't, if you put in too much material, then obviously there's going to be some of that material that's going to quote unquote fall out or precipitate out or recrystallize out. And that will naturally settle at the bottom of the vessel because it's, well, it might be denser than the material, than the solvent's material, for instance, water. If you're putting in sodium chloride, if that's more dense, then that will obviously settle at the bottom of the vessel. That indicates then that you have a saturated solution. So one way to define an unsaturated solution is to describe it as being, hey, look, you don't have additional solutes or additional kind of reaction products, any kind of solid at all that has essentially, quote, fallen out of that solution phase. Solute becomes solvated or hydrated when it dissolves into solution. And when it does so, but then it gets to the point where it actually precipitates, usually you have some crystalline material that forms part of that precipitate, but it's also not uncommon to have amorphous material as well. So just know that both crystalline and amorphous materials can be evolved in a saturated situation. Now, with respect to solubility, how does it scale with temperature, and is it same for all phases? So we briefly discussed in chapter 7 some of the different phases, solid, liquid, gases, and their interplay of moving from one phase to another. Here, I want to bring your attention to gases dissolved in water. Generally, as it's shown here in this chart that I'm showing you, solubility decreases as temperature increases. So if I may, let's think about having bottled water. If I was to have that bottled water remain at room temperature, then a lot of that carbon dioxide, which is typically added into that bottled water, it'd be carbonated, would actually tend to fall out of the solution being water, and it would collect as a gas, and it would, occupy that head space between the lid and the top of the fluid. If I were to put that same bottle, and again, I didn't open anything, but if I were to put that into the refrigerator, then most of that CO2 gas that would have been, out of solution, quote unquote, would actually redissolve into the water. And so then whenever you did finally open up that bottle, you would hear more of a hiss as the water rushes to escape, because it has to first escape the liquid phase, then to the gas phase, and then to the, through the opening and into the atmosphere. So the pressure that would be created if you had already opened the bottle, exposed it, maybe you were drinking some of it, maybe you didn't have the stomach or the desired taste or whatever to drink the whole thing, maybe you left about half of it in there. If you had already opened that up and you consumed it, under normal atmospheric conditions here, and then reclosed it and then were to open it later, you would get less of a hiss if the bottle had just been sitting, you know, like on the countertop or something. But if you were to put that same bottle with half as much material in it, because you had already sampled from it, back in the refrigerator and then pulled it out later to drink it, as soon as you open, you're going to have more of a hiss because there was a greater dissolution or solution of gas within, you know, dissolved gas in that solution. So it's just an interesting characteristic of gases in water. You can see in this graph here, you have methane, oxygen, carbon monoxide, nitrogen, and helium. Carbon dioxide is not shown in this figure, but you could make a reasonable approximation here that carbon dioxide would also follow the same trend line, and it would probably occur somewhere between carbon monoxide and probably, you know, oxygen. So just wanted to share that with you. Basically, as things get warmer, then it's less likely for the gas to remain in the solution. And again, I just talked about bottled water, but this is another reason why, for instance, if you were to have a carbonated beverage, you would opt to have ice added to that beverage. It'll actually keep the quote unquote bubbles or fizz in the solution, and it won't taste as flat, or it won't go flat, quote unquote, as quickly as what it would if you just had just the soda or whatever carbonated beverage that you had and you just put it into a cup with no ice. If you don't add the ice, then you can't get that pop, that fuzziness, fizziness to last for a longer period of time. So that's an interesting, I don't know, just life knowledge there that you might want to apply if you enjoy having carbonated beverages and you like that fizziness. Well, opt it for, you know, keeping it cool with the ice. And of course, the only drawback there is if it gets too warm, then the ice melts and that waters it down. So I guess you just have to balance that factor out. But that just helps you. If you know you're going to enjoy the soda in a relatively short span, meaning that the ice cubes won't melt and therefore water down your beverage, and at the same time it would also then warm up and then more gas would release, and then it would just taste nasty, I guess. So watered down fizz-free soda is not something that's enjoyable, but that's just an interesting observation there. That's another reason why some breweries actually, if you were to have beer, right, they would actually frost the glass first. So you could presumably do that with any kind of carbonated beverage, not just beer. You could do that with your soda if you wanted to, or your water, your carbonated water, if you like that. But you know, having like a frozen glass or putting the glass in the refrigerator to cool it down, and then pouring the beer or whatever carbonated beverage you had in that glass so that there's no ice available. I mean, that of course is another way to actually maintain that carbonation effect and therefore that kind of taste. So just an idea. Methane clathrates, interestingly enough, do exist, and it's really interesting because it's actually methane gas that is trapped within ice clusters, and the ice clusters, because they're very dense and they form a solid network, we can all think of ice cubes or even glaciers, you know, from those two different size scales. You can imagine then that it's completely reasonable to have gases that could occupy those glass or those ice structures, and these clathrates are an example of that. So in these images here, I have just this methane clathrate that has not been set on fire, and you can see the honeycomb almost looking like structure that would be reminiscent of something that ice could produce, because it does have kind of a hexagonal kind of macroscopic and microscopic ordering. But again, that depends on pressure and temperature and everything else. And usually the stuff is found closer to the ocean floor. So you're not going to find these methane clathrates at the Earth's surface per se, at the normal surface. So you kind of got to dig down. So these might be on the bottom of ocean floors or in, you know, way beneath some glaciers, or land trapped underneath a glacier. You know, in other words, where there's going to be significantly greater pressure present, because the pressure combining with the temperature, and then of course if there is any kind of gas that has evolved due to, I don't know, just natural methane evolution, just from chemical processes or biological processes too. Anyway, that can happen, and this is a source of fuel. And so in the image on the right, you see this flaming methane clathrate. It's flaming because methane is the actual fuel. So you can light a match and hold it up, you know, just hold it near this methane clathrate, and and the methane that was trapped, I mean, obviously, you know, you might have to heat a little bit of that ice just to form, or just will break open an opening or whatever, but it can definitely produce a flame. So kind of interesting. You guys know that solid phase, which is ice, is less dense than the liquid phase of water. So that's pretty interesting. So as gas is dissolved in organic solvents, this is way different. Solubility increases as temperature increases. So this is really interesting. So the solubility of gases, if it's not in water, which water, you know, shows in this upper left-hand graph where you have solubility decreases as temperature increases. If you have the same gas and you applied it into like, I'm trying to think, how about some pentane or hexane or benzene or your automobile fuel oil, the solubility of gases would actually increase as temperature increases. So it's kind of an inverse relationship, and it speaks to the differences and the power of water. And one of the reasons is because of that hydrogen bonding like power that water naturally possesses. So kind of interesting. Now with respect to solids, it's pretty clear. Solubility also increases as temperature increases. So I think that is very clear. So for instance, a practical example, if you had tea or coffee and you don't prefer the bitterness of that, then you can always add some sugar. And if it's warmer, it dissolves faster and better actually into your tea or coffee solution. So what about solubility versus pressure? Well, for gas-liquid interface, here we can talk about Henry's law. And Henry's law states that as solubility increases as the external pressure at the gas-liquid interface increases. In other words, contents under pressure, right? So if you take this image of a carbonated beverage and you see that it would be in a can and it was canned with carbon dioxide and it's sealed completely so the gas molecules can't go anywhere, well, then they're going to remain dissolved within that can. I mean, in that can, there's not a huge amount of headspace that's going to allow for that carbon dioxide to occupy. But as soon as you open that tab, the pressure of which inside the can is greater than the atmosphere, that's why the gases are going to want to go from the can to the atmosphere, then the pressure is going to be released. If that happens, then the carbon dioxide bubbles are readily going to want to shoot out from this pressurized environment. And you will then have fewer gas molecules remaining in solution, especially if this is at room temperature, right? Because we know that soda has the solvent of choice in soda, of course, is water. It's not benzene or alcohol or anything else like that, but it is water. So we know that the solubility will decrease, right, as temperature increases. So that is Henry's law, basically. Solubility increases as external pressure at the gas-liquid interface increases. But in other words, at the gas-liquid interface inside that can, the pressure is pretty high, so the solubility is going to be high, right? You open up the can, you remove that external pressure process there. So it removes the pressurizing atmosphere, and you get loss of then your solute, which was carbon dioxide. If we were going to talk about the biological application of Henry's law, we could use respiration as an example. Oxygen dissolved in the blood increases as lungs expand. So in this example, if you breathe in, you see the directions of the orange arrows. They indicate that you have carbon dioxide and oxygen intake, right? A lot more oxygen intake than carbon dioxide. You're looking at the pressure here, 160 millimeter mercury of oxygen versus the pressure of the carbon dioxide. It amounts to about 0.3. Why? Because you're not breathing in pure oxygen, right? If we're breathing in atmospheric air, actually, there's also nitrogen present. There might be a bit of hydrogen present, and there's some other gases too, including carbon dioxide. Anyway, the oxygen will move into the bloodstream, and the pressure of the oxygen in the bloodstream is about 100 millimeter mercury. So as oxygen is dissolved in blood increases, the lungs expand, right? Increases. Everything scales like that. Now, if carbon dioxide dissolved in the blood decreases, lungs then are also contracting, right? So breathing out. Here in this particular case with the blue, the CO2 moves out of the bloodstream. You have 40 millimeter mercury of pressure of carbon dioxide from the blood enters in the lungs, and then it's going to leave, right? It's going to be exhausted. So that's just one of those examples here, biological application regarding a pressurized environment. So hopefully that remains pretty clear. Respiration example, Henry's law. Here's problem 8.4. We can actually talk about this a little bit further. So will the pressure of oxygen in the bloodstream increase or decrease according to this situation? Climbing to the top of the 10,000-foot mountain. So at the top of the mountain, is there higher or lower pressure? Well, we already know from our scuba diving examples, which we did especially in chapter 7, that the deeper you go below the normal Earth's surface here, like the beach or boat surface, if you were going to jump off a boat, as you go deeper into the water towards the center of the Earth, the pressure increases. So if you're at the top of a 10,000-foot mountain, you don't have much pressure on you, right? So this is how you can answer that. So just know how the air pressure naturally changes as you move from where you currently are looking at this video. You're at the normal Earth surface. Imagine either up high in a mountain or down below in the ocean. And so you can then consider Boyle's law, where you have pressure is inversely proportional to volume. So since the altitude has increased, the volume has increased, right? And the pressure then must decrease. So this is a way of using Henry's law to also try to help explain this. Again, this is just a thought experiment, really. We haven't put any kind of numbers to this, but if you were to work out an example where there were numbers, you would want to come up with a sensible answer. And so you would expect then the pressure must drop. And this is one of the reasons why, at higher elevations, sometimes generators don't work as well. Sometimes your breathing doesn't work as well. And even in an automobile, maybe especially if it's not fuel injected, but if carburetor systems are still used, or even diesel systems are used too. I mean, the fuel oxygen mixture is going to matter incredibly, and at elevated points where you are going to have some kind of fuel being used, then it could be possible that you might not be able to have a very efficient, running system. In other words, the engine might choke or it might just sputter out. So with pressure of the oxygen, remember how we had dissolved in the bloodstream, that will tend to decrease then, only because we're at a high altitude. And volume is related to what? Area times height, right? And height being equivalent here to the altitude. So if the altitude is like 1 foot, if you're normally at the standard surface level, right? Especially here in Indiana, you're not going to have much of a problem. But if the height increases to 10,000 feet, your volume is going to increase, which means your pressure will have to decrease. Again, this follows Boyle's law. So with respect to an unresponsive person, so somebody might be in shock, receiving mouth-to-mouth resuscitation, which is done to kickstart respiration, will the pressure of the oxygen in the bloodstream increase or decrease? Well, since the amount of oxygen forced into the lung will transfer to the bloodstream, then the pressure of oxygen will have to increase. So you could either use, mouth-to-mouth, or one of those ambu bags where you have like a manual pump that you just keep on pumping with your hand pumping in order to force air into the body, hoping that oxygen can get to the lungs and then therefore to the brain, of course, and to other vitals. The oxygen will necessarily increase. All right, Henry's law and decompression sickness. So this is something that I just want to cover briefly because it's interesting from a diving perspective. After diving at depth, scuba divers must slowly ascend to prevent what's called decompression sickness. So what does this mean? Well, this slow ascent involves a safety stop to help nitrogen and other gases safely clear the bloodstream. Otherwise, this can happen. Decompression sickness will arise if you get bubbles of air that are not oxygen that are getting trapped in your bloodstream. And in this particular cartoon, I show you nitrogen gas trapped there. Usually, this is called an air gas embolism, meaning that it's a condition caused by gas bubbles in the bloodstream. And if it accumulates in large amounts in the arteries, then the bubbles can stop the flow of blood. You can clearly see how that can essentially blockade off the red blood cell communication of oxygen, which it needs to get to the lungs and then therefore to the other parts of of the body as well. But without oxygen, then you're going to have cell death. Usually chambers are utilized, pressurized chambers, where controlled amounts of pressurized oxygen are then delivered to somebody who might be experiencing decompression sickness. Usually they're going to be in there for quite a while. So it's a very slow process. It could be a very expensive process, but there are methodologies to have somebody safely recover in the event that they are having these kind of symptoms, meaning that somebody might feel very sick, they might feel dizzy, they might vomit a bit, they might not have a good recollection of certain events. So those are all some of the symptoms that decompression sickness could be occurring. And I'm just showing you here these hyperbaric chambers, like I'm showing you this air ox here chamber, usually provide an environment that will give, I don't know, greater than or equal to 1.4 atmosphere. It's a hyperoxia environment in order to counter the events of what's called, if you have not a lot of oxygen, you call that hypoxia. All right, so let's move on and talk about solutions, suspensions, and colloids. And I say, oh my, because I can't help but do that. So if you have a solute that's been admitted into a solvent, if it dissolves, you guys already know, then that's going to be a nice solution. If it starts precipitated out of that solution, then it'll be quite saturated and things will be, recrystallized. So solutions will be nice. Solutions will be very, very easy to, diagnose essentially or detect. The solute dissolves completely, no precipitation. It ought to be clear and transparent. You should be, in other words, you should be able to look straight through it. Even if it's a blue solution. So say some of you like making flavored drinks, right? You pour in the sugary or sugar-free, I guess, concoction if you want to make lemonade or some kind of like Kool-Aid type of beverage. If you're able to still look through it clearly, even though it might have a pigment of a red, pink, blue, green, whatever, orange, as long as it's clear and transparent, you have a solution. Components that do not separate. So usually you would have to completely mix up a bottle of Italian oil dressing, right? Because it's made with oil and water. Usually the oil is in water. And so you have these emulsions, you have these little fat bubbles, right? These oil bubbles that have developed in the water if it's an oil and water emulsion. You'd have to shake that up. So that would not be an example of a solution. Homogeneous mixtures are solutions, and solutions here can refer to solids, liquids, or gases. So this is pretty interesting. So you can have, if we're talking about solids, some interesting, scenarios. You might say, well, these are not clear and transparent, but this is also not a liquid. So clear, transparent liquids are expected, but with respect to solids, it can be all one complete homogeneous mixture phase. So here's an example of a solid mixture phase, like these brass keys, right? You obviously know about, soda. You obviously know, just from me talking about a little bit of the scuba and the scuba apparatus and whatnot, and the air that we breathe. These are the cylinders, and these are how much oxygen and nitrogen could be present in some various cylinders, but they're not divided like that, right? There's not a demarcation where nitrogen is, at the bottom third of, or bottom half of the cylinder, while oxygen's only at the top. No, everything's mixing in. And of course you can have glass material, which is a version of a solid, but you see that it is still colorful while being transparent. So those all would describe solutions. What about suspensions? Here we have insoluble particles in solution. Generally, they're non-clear, meaning that they will have some turbidity or haziness to them. They can have color. They will scatter light because light will scatter from the individual particles. The particles in there are generally greater than 1 micron. And you can have heterogeneous mixtures, and phase and component distinction separation is expected. So how would you be able to look at this? Well, what if you froze, for instance, olive oil, and it became a solid, and you immersed it in a liquid olive oil? So even though you still have olive oil, if there is a phase distinction between those two, one is solid while one is liquid, that would mean that you have a suspension. Even if you have water, right? So even if you have a block of ice, right, in water, you can still have that distinction there. Usually, if you were to centrifuge out blood, right, you would get a separation of different phases. Here in this cartoon in the bottom left, they say that the plasma will be nearer to the surface, it'll appear yellowish, and the heavy blood cells will sink to the bottom. That will appear the deep red or even maroon. And here's an image actually of what blood would look like after centrifugation. So, or centrifuging, or however you want to call it. Now, usually if you want to donate plasma, then only that yellow will go towards that. If you want to donate the red blood cells, then only the maroon part would be donated. But usually this lighter stuff with the plasma has a lot of other interesting things that are very important, like white blood cells, and they have some physiologically important solutes in there and whatnot. And here in this image, try to give you this cartoon here in the bottom right, try to give you an example of what that would look like. And there's a little description here that there's even white blood cells that are actually residing in between the red blood cells and the plasma fluid. Plasma fluid generally occupies about 55% of that clear yellowish-like fluid. In fact, within that 55%, 91% is water, while you have 2% being nutrients, 1% hormones, electrolytes, 7% blood proteins. So pretty neat stuff. And there's also some platelets too, quite near where the white blood cells are. So usually those are mixed in. So blood is very complicated, and you would consider it then to be a suspension because you're able to get those distinct phase separations to occur. So blood is a suspension. It's not a solution, and it's not a colloid. Which brings us to colloids. And colloids, I mean, all of these are very familiar to us. So it's not like, solutions are more common in everyday life than suspensions or colloids. Actually, these are all equally as prevalent as one another. So when we talk about colloids, it's insoluble particles in solution. They can be clear or opaque, but likely to have color. They scatter light because there are particles in there. Usually proteins and fats are present. Now look at, the particles tend to be smaller than that of the suspension. So you're talking less than 1 micron, all the way down to say around 1 nanometer. Heterogeneous mixtures are another indicator, as well as phase or component distinctions, though sometimes difficult to detect. So in this particular case, you have here a solution that looks like a solution, but in fact, whenever light is applied, you can actually see that there are tiny particles in the glass vial on the right-hand side. The left side was just a control, didn't have those tiny particles, but you can't see them unless you have light illuminating on that, because light, scatters off those particles. So there's very tiny particles, smaller than 1 micron, that will generally give rise to the colloidal looking appearance. Proteins and fats. We know that in milk, there are proteins and fats. Milk is a type of colloid, and the particle sizes are generally smaller than 1 micron. They might be a little bit larger, but again, you're having a lot of insolubility and you're having a larger amount of proteins and fats present. If you were to add milk or some kind of cream to a coffee, right, then you would actually create a colloidal environment. You're going to have, again, because you have proteins, you have fats, you have something that's going to be very distinct in and of itself, and that can be residing completely independent, right? You have these colloidal, environments that become established whenever you add a colloid like milk to a coffee milk combination. So colloids, before it's mixed thoroughly, right, will exist in the coffee. Another example is mayonnaise. Another one's Italian dressing. Cheese, because milk has a lot of protein and fat, as does cheese, and these particle sizes tend to be less than 1 micron, and that they are difficult to detect once they're all pretty much blended up. The phase separation is not so very clear, and you're going to have that. You have cosmetic creams are a lot of that, and even, for instance, smog or smoke. Generally, you're talking about less than 1 micron of particle size. And of course, you can also have paint as another example. So lots of different examples. The Italian dressing is the only one that's a little bit weird in terms of trying to figure out if that's a colloid or not. You could consider that potentially a suspension, I guess it would depend on the nature of the Italian dressing, and this one looks way different than all these other ones. So I wouldn't put too much stock into this one, but if you were to ask and say, hey, is Italian dressing a solution, a suspension, or a colloid, generally you would consider that to be a colloid, but that's, but that one definitely has some asterisks to it then, because it depends on the constituents of what that Italian dressing is. All right, so you have solutions, you have the suspensions, you have the colloids, you have some differences in all of these solutions. So now let's talk about electrolytes. And we got to go back to talking about reaction chemistry again. Reactants are going to come together. They need to be drawn close enough together that they form products, right? So you have magnesium chloride as a salt, and if that was put into water, because this is an ionic salt and water is a very polar solvent, you have the ion dipole intermolecular forces that arise, and the salt readily dissociates and then leads to what we consider to be a strong electrolytic system in which it can power, for instance, a light bulb. If you had sugar, for instance, like what I'm showing here, then if that were admitted into a solvent like water that was just digested, and this one isn't, I guess we have to be clear here. I mean, this is probably glucose, for instance. That's not going to illuminate the light bulb. This is not dissociating in any way. It is polar and it's interacting with water, which is also polar, but they're just really hydrogen bonding kind of forces, not the ion dipole. The ion dipole are stronger than the hydrogen bonding intermolecular forces, and because nothing is dissociating, no ions are being created, you're not going to get that illumination. So this would be considered a non-electrolyte. Well, what about vinegar, like acetic acid here? That is a weak electrolyte because it weakly dissociates. You have some of these protons that become separated from the acetate, from the acetic acid molecule, generating acetate, which is negatively charged, CH3COO negative, as well as that proton. So electrolytes, if I were to use these examples, what's one of the key properties of them? They generate ions in solution. So that is hugely important, and this is going to be based then on the ability for at least one of those atoms to break of the solute atoms to break away from the rest of the molecule. In this particular case, hydrogen breaks away from vinegar. If we're talking about acetic acid on the right here, it's going to break away. In doing so, it becomes ionized. That gives rise to a weak but noticeable electrolytic property. If we're talking about the ionic system of magnesium chloride, well, that's a strong electrolyte because both agents just want to completely dissociate in solution. So you have magnesium and chlorine in high abundance. That's going to be a strong electrolyte. Again, the dissociation is the degree in which the solute dissolves to produce ions. We will definitely come back to that later when we talk about acids and bases. But let's take a look at magnesium chloride a little more closely. So you know that if magnesium chloride were to dissolve in water, it would form magnesium ions and chloride ions, right? And that's how you would write it, and of course you would balance it. The charges must also balance because this is conservation of matter properties, and it also pertains to ions. The charge of the solids and liquids and gases generally is going to be 0, and the charge of the aqueous solids is also generally 0. So all you got to do is look at the charge of the reactants. If that's 0 on the left-hand side, then on the right and left-hand side, they must add up. Those individual ionic charges, whether they're positive or negative, must sum to 0 if you're starting with 0 in the reactants. So in that particular case, you have that 1 mole of magnesium that has a +2 oxidation state, right? And 2 moles of chloride, which has a -1 oxidation state, they sum to 0. So ionic compounds dissociate, pretty clear. For a non-electrolytic system, let's take a look at glucose. It still just remains in water, but notice how we change the phase. Instead of just solid, because it's not just glucose, either liquid, if it was emitted as a liquid, or even sugar, a solid phase, it's not that anymore because it is hydrated, it did dissolve. Those hydrogen bonding intermolecular forces did lead to this dissolution, this like dissolves like, and so the phase does change. It's not just solids. You can't just see the solid in solution. It's aqueous now, AQ. Again, looking at the charge of the solids, liquid gases, and the aqueous solids, everything's 0. Now, covalent compounds do not always dissociate, and that's another way of differentiating ionic versus covalent compounds. So here, you still got some dissolution. The covalent compounds do not dissociate. We don't see that this has a very strong electrolytic property at all, and that's just what you get. So glucose is not an electrolyte. If we were to look at weak electrolytes like acetic acid, you can look at this. So, and again, we're going to be visiting this in the next chapter, which is coming up, shortly here. I mean, we're already in chapter 8. That's going to come up in chapter 9. You have bases and you have acids. So you have carboxylic acids as the base, and you have an amine as the neutral form of the base. So if it becomes charged, it becomes a protonated amine. Sometimes it's called quaternary, amines. You also have the carboxylate form. If it's charged, doesn't go positive, goes negative. So with that understanding, if you were to put then a carboxylic acid in water, it would dissociate to its carboxylate form. If you were to put amine in water, it would dissociate and actually form a protonated amine potentially, okay? So in this example, we're using vinegar. So what is vinegar? Or I'm calling it vinegar, it's acetic acid, which is essentially the quote unquote active in vinegar. If we were to put acetic acid into water, it would dissociate into the acetate, the carboxylate form, which is the negatively charged species, as well as that proton that had to get separated. Charges, again, must always balance. So the charge of acetic acid is 0. If we're looking on the left-hand side there, on the right-hand side, acetic acid anion and the proton, so you have the acetate and you have the proton, negative and positive, they are also going to balance. So that's clear. They do dissociate, acids and bases do. It doesn't have to be a strong acid or a weak acid or base. As long as there are ions that can evolve, while they may not give you great illumination in this example, because they may not be, great electrolytes, they are still electrolytes nonetheless. And so here you might want to reference the battery demo that I assembled, and this is what this slide is about. So you can look on my website for the orange powered battery is what I call it. And in this image here, you see a blue light, and that's an LED, okay? And that was powered by about 2.4 volts is what I was able to generate from these 3 batteries. In order to get that to make sense, and by the way, you can use other citrus fruits. You can use lemons, you can use limes, probably mandarins, clementines, all these things. You might have to use more or less fruit depending on the size of the fruit, depending on the freshness. Like these oranges, these were about, I don't know, a month old. They were actually getting a little bit hard. I also did this with lemons. They also worked quite well, but the lemons were even older. I think they were about 6 weeks old. But, even though their peel was still very, very hard, almost getting hard like not baseball-like, but almost. I mean, there was no pliability whenever you could squeeze it and put pressure on it. But there was still enough citrus juices in there that it could still, if I were to connect them in this battery kind of setup, they would produce illumination. So in this particular case, we're looking at citrus fruits because they have citric acid. Again, you know that citric acid is a carboxylic acid. It is a weak acid, but it does lead to dissociation. And under an acidic environment, meaning pH is really low, again, we'll talk more about pH in chapter 9, that's coming. But you can see that the acetic acid dissociates, is what we call, into a proton and the citrate anion. What's really interesting here, and which is one of the reasons why I was able to do this with just 3 oranges, and in fact, I was able to do this even with just 2 lemons or even fewer than that, depending on the size of the lemon, is that I use magnesium. This is interesting because magnesium is so reactive. It's way reactive, more reactive than copper, and it's more reactive than zinc, aluminum, and some other very common metals, especially in the presence of acids. And so I used a magnesium rod in this photograph here, and you'll be able to see that more clearly if you watch the video that I have on the site. I think there's a link that I actually include here to the YouTube video. The black jumper is actually affixed here with an alligator clip to to the magnesium rod. And as soon as the magnesium, even without any kind of battery hookup at all, as soon as that magnesium rod is placed in the orange, all of a sudden you can start you hear it, and you can also see some of the reaction starting to unfold around that magnesium. If I were to let that magnesium rod in there for, I don't know, even 2 hours, you're going to get, I would actually see a lot of elimination, reduction of the bulk amount of magnesium that I started with. So there is a reaction, and the reaction is magnesium reacting with the citric acid. Magnesium ions are produced, and so are electrons. And electrons are one of the ways that we're able to actually generate this power, because from any kind of battery, even if you take a 1.5 volt standard battery that you would put in a remote or some kind of mobile device that would still use it, even if you had a Walkman. Maybe some of you don't even know what a Walkman is, but years ago they had Walkmans, and they would take like 2 standard, what they would call AA batteries. You guys are very familiar with AA batteries, but each of those are about 1.5 volts, right? It's all about the electron transfer from one end to the other end. And so in this example, you have magnesium that is driving the electron evolution because it's being dissolved fairly quickly in the citric acid. So magnesium is reacting with the citrate. Again, the citrate already exists in that fruit by virtue of its citrusness, right? And it's a low pH environment, meaning it's less than 5. Lemons, I think, are even less than 2, so it's very acidic. That's why they tend to make even better batteries than the oranges, but just wanted to use the oranges. These oranges, actually, one of the reasons I wanted to use them is I was actually curious about testing the ability of these quote unquote low acid oranges. And they were still pretty acidic, but not nearly as so as I guess as the quote unquote typical orange. But you can see that although they may be marketed as low acid, there's still enough citrus acids in there to power a blue LED light. Anyway, so then the hydrogen cation, right, the proton that was generated is going to react with some electrons that have been evolved from the magnesium, and hydrogen gas can be produced. Now that is one of the possibilities there, but also on the other side, you have copper, and copper I had attached to the red jumper, and copper itself also leads to the evolution of, or has those electrons that are traveling from the magnesium side of things over to the copper side of things. So those 2 electrons that are being accepted by copper actually is going to be able to generate the hydrogen gas at the copper electrode. So to be able to better understand that, here's a battery diagram. Maybe this makes sense. But you're going to have more of the hydrogen gas evolution at the copper electrode than you will at the magnesium electrode. I tried to show that in differences in size. I don't know if you can clearly see that, but there's going to be less hydrogen gas evolution at the magnesium electrode. It'll still happen because there's still protons available, and electrons are, after all, originating here. But the electrons will be generated, they'll be moving across the way. If it's connected in a circuit, which I did here with 3 batteries, everything's connected all together. It's going to power that light bulb or the blue LED in this particular case. And the electrons, any excess, will still continue to travel to the other electrode. This is how batteries work. But whenever those electrons are collected at the copper electrode, the copper isn't really dissociating a whole bunch. I mean, right above this battery diagram, I show you that copper and citrate could theoretically react together to form copper citrate, but really it's not a very reactive situation. Copper is one of the least reactive metals when it comes to transport of electrons in acidic environments. So I think that's really important. Although it's very reactive to oxygen, for instance, we know that, right? Copper can readily oxidize, and you get that green patina, i.e., or e.g., the Statue of Liberty. With respect to acids, it doesn't really have as much of a reactivity as, say, for instance, magnesium does. So you're not going to get a lot of that interaction with the citrate and the copper ionic species. So what happens to those electrons? If they're just sitting at the copper surface, well, they're going to react with available protons that originated from the citric acid. They come together, they form the hydrogen gas, and so you'll get little bubbles. If there is little, if there's an opportunity to see bubbles maybe trapped near that boundary of the copper wire inserted into the orange or whatever citrus fruit you want to use, you could actually see some of that. So that is a possibility. So this is just the summary then. Magnesium is very reactive and will rapidly break down. Some of those hydrogen bubbles at the magnesium orange interface surface due to the protons from citric acid and the electrons evolved from the disintegration of metal, but that's not going to be very prominent. However, lots of magnesium citrate will form. In contrast, copper isn't very reactive, and more of those hydrogen gas bubbles at the copper interface with the citrus fruit, just due again to the presence of the proton from the citrate and the available electrons that travel from the magnesium through the LED and are terminating there within the copper. So very little copper citrate will form because it's not as reactive. Now, just to let you know, what is serving as like the medium in which this is all going to happen, it's going to be the citrate flow and perhaps some of the electron flow, but you're going to get all that citrate just moving right across. It's going to be attracting to the positively charged magnesium ions that are created through dissolution of magnesium metal. So I call that the citrus matrix in this particular case, but that would be the example there. So pretty neat situation, I think, in terms of what we're looking at. Now, the next part of this is looking at concentration, and I think we're going to stop here for a minute and we will revisit it. I think there was a lot of material that I covered here, so we will start covering. Hopefully we can wrap all this up, all the different concentrations, including dilutions and things like that you're going to be dealing with in your homework and even in the exam later on. So look for part 3 then coming up shortly. Thank you for your time, and that's it for now.